the goal of this research was to improve the energy efficiency of our microprocessors. So that can either equate to improving the battery life of a laptop or a tablet, or actually it can scale up to a server where we want to improve the performance in a fixed power budget. So what we found was one way to improve the energy efficiency is to reduce our operating supply voltage. And what we found was as we reduce our operating supply voltage, our power drops much faster than our frequency as shown in these two graphs. And our energy efficiency improves. And it improves to a peak energy efficiency point near our threshold voltage, near the threshold voltage of the device. And the threshold voltage of a device is the voltage at which the transistor turns on. Basically, this is why we call it near threshold voltage computing, because we're operating near the threshold voltage. And what we did was we implemented, kind of for the first time, near threshold voltage circuits on 22 nanometer Tri-Gate CMOS. And we implemented a SIMD vector permutation engine targeted for ultra-low power graphics for tablets and handhelds. And we implemented novel circuits for both compute and memory. So we have the logic and memory on one single supply rail, and we scale that supply rail down to near threshold voltages. So both the memory and logic can operate at ultra-low voltages. And our prototype showed a very wide operating range, and it also showed a 9x measured energy efficiency improvement. We actually published this work at ISSC 2012 back in February, and we were the recipient of the 2012 Distinguished Technical Paper Award. You want to know? So this is a wafer, 22 nanometer Tri-Gate wafer, and this is a video of our lab in Hillsboro, Oregon, showing us some actual random vector tests that we run on our prototype at near threshold voltages. And what we're doing here is we actually wafer probe our experiments, so we directly land on the wafer to run our tests.
Thank you very much.